Today I will be telling you about orbital degeneracy lifting in a strongly coated electron system, which is sort of our step forward in exploring the precursor states at high temperature in various materials. This work has recently been published in this paper, and I wish to acknowledge our funding sources as well as the resources we used to do our experimental work, as well as to acknowledge the invaluable contributions of various collaborators from 4 different institutions that I list here. The samples for this study come from Haidong Zhu from University of Tennessee in Knoxville. Okay, so that being said, this is the outline of my presentation. I will be talking about so-called ODL precursors. So I will give some broader context of what we are actually after. And I will follow that with the recapitulation of some earlier ODL observations that actually, as a matter of fact, presented in this very conference last year. And then the main subject will be this system sodium titanium silicon 2 oxygen 6 pyroxene, which is a multi-insulator. I will show you the structure and properties and then demonstrate how we detected this ODL-like precursor behavior at high temperature. So to start in a sort of cliche way, the emergence of technologically relevant quantum orders and the associated rich physics in quantum materials originates from complex interaction of electronic degrees of freedom, charge, spin, and orbitals, and their interaction with the host lattice. And usually this results in some kind of complex phase diagram. And in principle, complexities of ordered phases are extensively explored and to a large degree in many systems understood. However, proportionally less is known of what happens in the regime away from those ordered phases. In transition metal systems with partial filling of d manifolds, novel properties often engage orbital sector, and this is significant because orbitals couple both to the spin and to the lattice. And then of particular interest are systems with lattice symmetry imposed electronic instabilities such as orbital degeneracies and or electronic frustration. And this comes about because removal of these instabilities, orbital degeneracies and relief of frustration impacts symmetry, lowering and affects materials properties. The mechanisms of orbital degeneracy lifting are numerous: crystal field, Young-Teller, molecular orbital, spin orbit coupling, and so on. And sometimes they compete, sometimes they're acting in cooperation. In the systems where orbital degeneracies are anticipated based on their relatively high symmetry of the ordered structure, crystallographic symmetry lowering, let's say at temperature-driven structural phase transition, is often assumed to imply simultaneous orbital degeneracy lifting. However, this is not always the case. So usually in materials, high temperature phases are characterized by undistorted high symmetry crystal structure, which imposes, as I said, orbital degeneracies and related electronic instabilities. And then one can ask a question of what actually happens locally at high temperature, or for that matter, anywhere in these phase diagrams away from the ordered phases. And to that effect, for somebody who is doing structure property type of studies like me, utilization of local structural probes often provides useful information, such as, for example, studies using total scattering-based PDF methods, that we do. So we usually study local structure of materials on polycrystalline samples using conventional X-ray PDF and neutron PDF approaches at these facilities. And more recently, we started adopting an emerging method, which is called 3D differential PDF approach, which is based on single crystal measurements. Okay, so last year, roughly at this time, I showed at this forum our results of our studies of orbitally driven pulse transition and metal insulated transition in weakly correlated spinels basically structure such as magnetite, cubic spinels, in which I show two systems. One is iridium thiospinel, which has half a hole per transition metal and has a metal influence transition just below room temperature. Ground state of which is actually a formation of these octameric molecules, a backbone of which is spin singlet dimer on iridium sublattice. There is actually charge ordering, orbital ordering, and spin dimerization taking place in this system. And then it's a sort of electron counterpart, which is titanium version of the system, which has one electron per transition metal and which in ground state forms these helical structures, again composed of titanium dimers in this case. And as it happens in these systems, high temperature metallic regime is actually highly anomalous, as can be seen by a number of properties. So for example, here I show thermal conductivity, which is glass-like at high temperature, as well as relatively actually poor conductivity in this titanium system. So people have speculated that this is possibly because the spin singlet dimers somehow in some local form persist at high temperature. So we utilized X-ray peer distribution function measurements. And so what I show here are two panels for the two materials. On the left-hand side, you can actually see structural signatures of this spin singlet dimer state in terms of unique features in the PDF function. And in both cases, these spin singlets actually disappear at the transition, basically showing that these are not actually the reasons behind poor metallicity and various anomalous properties. Instead, what it turns out is that there is actually a signature in PDF at high temperature of a different type of distortion, different than spin singlet dimers, that exists and persists all the way to the highest measured temperature in both systems. That has a relatively limited correlation length of the order of sub-nanometer length scale. So we basically have a large distortion that corresponds to spin singlet dimers that get replaced by a smaller distortion, which we call here ODL. And what this is essentially there is a covalent kind of bond between two transition metals in case of iridium system, or two such bonds that extend or span three transition metal sites in case of this magnesium titanium 2 oxygen 4 spinel. So we, for one of those systems, studied actually local structure using three-dimensional differential PDF method, in which you collect basically maps of intensities over a broad range of reciprocal space. You punch out the information about the basically punch out bragg peaks that carry information about the average structure, and what you end up with is basically maps of diffuse scattering, which sometimes show interesting patterns. So this is one cut that shows bow tie type of signal reminiscent of that seen in spin or water ice. And then if you Fourier transform this into direct space, you end up with a differential PDF, which is shown here as these three quadrants in white. And the strongest differential signal corresponds to the iridium-iridium sublattice. So this is basically Z0 cut. And so if you take a look down this line, what you see is basic differential correlations of iridium sublattice for nearest neighbors and next nearest neighbors of iridium. And you see immediately that this signal is quite different for the two types of neighbors. In the case of next nearest neighbors, this signal is highly symmetric with these blue wedges and intensity in the middle, whereas the signal for the nearest neighbor is actually asymmetric, with some intensity appears to be missing towards the origin of the direct space. So I'm not going to actually talk much about this. This is still sort of work at its final stage. This is just a teaser. So what we actually did to try to understand this is we did large atomistic modeling or simulations using molecular dynamics and Monte Carlo type approaches. And so an outcome of that is that this type of symmetric signal can be attributed to strong correlated motion, which basically tells you that these units are actually strongly bonded over some length scale within one unit cell, which is about 10 angstroms or so. And then In addition, for this nearest neighbor interaction, you essentially have a displacive component. This is how it looks like from ice rules displacement model that we actually utilized. And so if you combine the two, you end up with something that is observed in the material. Okay, so anyways, this is sort of just background. So in dimerized systems, this type of ODL state has specific signatures that define sort of a scenario. And this is as follows. In principle, in properties, away from the ordered phases should exhibit anomalies that are indicative of disorder. Usually spin singlet dimers that are ordered at low temperature vanish at the transition upon heating, but you end up with some residual local distortion that persists above the transition and deep into the high temperature regime. Those distortions are smaller than the dimer distortions. This state is discontinuously connected to the ground state, meaning that you cannot actually treat the transition as order disorder. And then those structural correlations are of limited spatial extent, usually sub-nanometer, as I said. This type of behavior is not limited to dimerized systems. Something similar has been also seen in metallic systems, superconducting rather, such as iron selenide, which is, as we know, the simplest structurally, it's actually the simplest iron-based superconductor that has a transition from tetragonal to orthorhombic structure at around 90 Kelvin. And this symmetry is, of course, related to C4 to C2 symmetry breaking. The transition is likely not driven by the lattice degrees of freedom because of the relatively small size of orthombicity. Instead, people have proposed that this is a transition driven by the development of a nematic electronic state, and that it's in some way the manifestation of orbital order. So early ARPES studies have revealed that across the transition, there is a 50 MeV or 600 Kelvin type energy scale that has been implicated. And one of the propositions was that this is a signature of lifting of X, Z, Y, Z orbital degeneracy at the M point. Magnitude of which is basically the orbital ordering that is onset at transition temperature. And then follow-up studies actually suggested that this is not so simple and that basically DXY manifold is also involved, and that this contributes to this 50 MeV splitting between DXY and the other two orbitals at M point, and the band separation is not intrinsic measure of the orbital symmetry breaking. At any rate, leaving sort of ARPES interpretation to the experts, we have looked at this system from the X-ray PDF standpoint at high temperature, at room temperature, and what we discovered is that the high symmetry tetragonal model does not actually fit the data that corresponds to the local structure, which can, on the other hand, be explained within the orthorhombic model that corresponds to sort of orbital degeneracy lifted state. Other groups have looked at that as well. For example, the work of Ben France and collaborators has given this map of orthorhombicity as a function of temperature and as a function of relevant correlation length. And you see that the correlation actually grows as you approach the transition. And then on the other hand, some finite correlation exists still at room temperature, and by extrapolation, you can see that this exists all the way up to possibly 500 Kelvin. As a matter of fact, we are doing together experiments to verify that. And then interestingly enough, there were also ultra-fast electron diffraction measurements, in which one thing that was anomalous that was observed at room temperature is that for early times upon excitation, there was an increase of certain intensities of Bragg peaks, which can only be understood as there being some kind of a nanoscale disorder that is being regularized by the probe as compared to the negative time delays, which suggests that there is some kind of a precursor to nematic regime at high temperatures in this system. So that's fine. We can kind of come to the question that we wanted to address in the study that I'm basically featuring here. And that is, are those ODL precursors somehow a peculiarity of systems that are close to localized to itinerant crossover or metallic phase? Is this necessary? Or can you actually observe such states deep in the MOT insulating regime where charge fluctuations are suppressed? And as it turns out, an opportunity to test this is given by this sodium titanium silicon 2 oxygen 6 pyroxene, which is a silicate mineral that is constituting the upper Earth's mantle, and is more popular in the sort of geological world rather than solid state physics world, although there have been some studies. Okay, so what is this system? Well, it's a strongly correlated MOT insulator that has about 2 electron volts energy gap. And it's crystallizing in this monoclinic structure, which features quasi-one-dimensional zigzag chains of skew edge shared titanium oxygen 6 octahedra. Titanium is in this system 3+, which means that it's in D1 T2G configuration with half a spin. And then it has double degenerate ZXXY manifolds, and YZ are sort of considered inert because they are separate by a small trigonal distortion. And then if you cool this system down at around 210 Kelvin, you have a structural symmetry lowering structural transition, as you can see here from powder diffraction profiles splitting and actually new reflections appearing. And then the system goes into a triclinic structure of this type that I'm going to talk about in a bit more detail in the next few slides. Okay, so these are the band structure calculations based on those structures, and you can see that as you go to the low symmetry phase, there is actually a lifting of the degeneracy of these relevant bands. On the other hand, ground state turns out to be non-magnetic with this spin gap of about 50 MeV, as evident from neutron inelastic measurements, and this result is consistent with the observed susceptibility. From the structural point of view, what is important is that actually there is a spin singlet formation of titanium dimers, and that results in structure in a distribution of short dimerized and long non-dimerized titanium contacts down this zigzag chain. And the transition is believed to be orbitally assisted pulse transition, where there is ferro-orbital ordering taking place. And then as you heat the system up, according to crystallography, these distortions disappear. You end up with a chain with homogeneous single-valued titanium-titanium contacts. However, a number of property measurements have shown that the high temperature regime is anomalous. The most prominent ones are broad phonon modes seen in inelastic neutron scattering and Raman spectroscopy that basically appear to just broaden and not really obey the factor group analysis. Also, these Raman modes at high temperature do not correspond to the modes observed in several sister compounds containing chromium and vanadium, for example, instead of titanium. And then also you have this glassy thermal conductivity at high temperatures. So people have speculated that this is somehow related to the disorder in orbital sector, that there is some kind of fluctuations in orbital occupancy or whatnot. But this was really never actually fully understood. We have done neutron powder measurements, and so I'm showing you this for one of our samples. So crystallographic models appear to fit Bragg data well, as you can see here on top and bottom. There appears also to be an intrinsic disorder in this system that is associated with this silica-like network, shown here as blue tetrahedral units. And that comes about from this diffuse scattering signal, which is temperature independent and results in sort of very strong silicon-oxygen bonding in this system, whereas basically the units are disordered throughout the structure. So you can think of this system as, from this standpoint, as one-dimensional chains that are relatively well isolated and that are embedded in some kind of a glass type matrix. As far as the diffraction goes, there is actually a anomalous jump in isotropic Debye Waller factors at the transition, which is a typical measure of onset of disorder of some kind. So we have done a complementary neutron and X-ray assessment of this. And so what I'm showing you here is actually simulations of the low symmetry, low temperature, and high symmetry, high temperature models of this material to see how the change will look like or would look like based on the crystallographic assessment. And we see that the change is quite dramatic both in neutron and in the X-ray case. Here I show it on the expanded scale over roughly 1 unit cell. And then here, the last two panels on the right-hand side are actually calculated partial PDFs that correspond to titanium sub-lattice, where you see dimerization in blue at low temperature. It goes into a regular sort of titanium distribution of distances. And the difference is this typical M-shaped kind of curve in the differential. Notably, the signal that comes from neutrons is about an order of magnitude smaller than in the case of X-rays. And that's not the only complication, as you're going to see, as far as the neutrons are concerned. So now I'm going to show you some assessment of complementary neutron and X-ray PDFs. I'm going to show you comparisons of data at in different regimes that correspond to the same temperature difference. So first we take a look at the data in the high temperature regime at two temperatures that are 70 Kelvin apart. And I plot the differential curve here. So this is for neutrons, and the bottom one is for the X-rays. And what you can see is that this difference is quite small, which corresponds to standard thermal effects seen in many materials. So it's nothing special. Now, if you do the same comparison of the data that correspond to 70 Kelvin or so difference, but that is those two temperatures are bracing the transition, you see that there is actually a quite dramatic response in the intermediate and the average structure, but the local structure appears not to change. If you kind of take a careful look, you see that basically the change in the neutron spectrum is of the order over the length scale of 6 titanium sites, which I mark here, are of the order of thermal change seen in the previous comparison, whereas it looks like the X-ray data are portraying slightly different picture, that there is actually some local change taking place as well. So we are going to take a look at how we would judge this system if we did not do the X-ray measurements, if you only did neutrons. And so this is how it looks like. Basically, the Bragg information gives you essentially a phase transition as expected for the average structure, whereas the local information, I'm plotting here different interesting distances and angles and so on, basically portrays an order disorder type picture, which turns out not to be the case. So this, based on neutrons, you would basically conclude that there are actually distortions similar to or identical to those corresponding to the spin singlet order dimer regime, which it turns out is not the case. Part of the complication is also that the distortion that is associated with the dimerization is opposite for titaniums that get closer together and lateral oxygens that move away, and the signal from this gets overlapped. Another aspect of neutron measurements that we did is we actually also studied the lithium sister compound to explore the effects of chemical pressure. And as it turns out, lithium is smaller than sodium, and as such, it contracts the lattice, which in turn enhances T2G orbital overlap and stabilizes the titanium dimerization, and also increases the transition temperature. We do see similar type of persistence of the local structure on some level in this system as well. But the most important message of this is that orbitals are indeed relevant for this transition. Okay, so now, as I promised, we are actually going to look at the rest of the analysis with X-rays. So first, I'm going to show you the comparison of X-ray data at different temperatures to basically demonstrate that the spin singlet dimers indeed vanish, disassemble above the transition. So here in this panel, we have temperature at low temperature data in blue and high temperature data just above the transition or at the transition plus in red, and you see that there is actually a tiny signal that corresponds to the spin singlet state. You can actually much better see it in the differential in form of this M-shaped curve. Now, if you do the same type of differential comparison, but for the two profiles that are similarly spaced in temperature, in the high temperature regime, you see that this signal kind of disappears. So you can track this differential as with respect to some high temperature reference data set. And you see that it actually evolves and disappears at around the transition temperature. You can quantify it by integrating it between some selected points, and you see that it clearly actually exhibits an order parameter-like behavior, let's call it that way, and that the spin singlet state vanishes at the transition. Now, instead of this qualitative, you can also do quantitative type of analysis or model-dependent analysis by fitting pair distribution function over different ranges, which gives you information about how the structure behaves on different length scales. So if you, for example, do a fit in this range between 15 and 30 angstroms in your data, you will see that your bimodal distribution of distances that corresponds to a dimer state goes away and gets replaced by a single valued distance distribution, basically telling you that the system becomes monoclinic at high temperature. If, on the other hand, you do the same thing for a narrower range of data, up to 15 angstroms, you do see that there is some kind of regularization going on at the transition temperature, but that this distortion actually does not completely go away. It actually gets reduced. This is much better seen if you look at the splitting of these distances shown here. So intermediate and long range structure behave canonically, whereas local structure sees that this splitting gets only reduced. And this, according to the sort of scenario that I presented before, is characteristic of this ODL type behavior for a dimerized system. So given that this is a titanium containing system that where titanium is in D1 state, this is very similar to a spinel system with titanium that I mentioned before, in which this type of behavior is understood by the following sort of cartoon, in which you have at low temperature, locally, you have a dimer state, which has a strong covalent bond with 2 electrons in it. And then this gets disassembled to basically obtain 2 ODL-like bonds, which are covalent bonds containing 1 electron. Now, this type of analogy has actually is problematic because in this particular case, because we're dealing with the quasi-1D system, and because this type of mechanism would imply that you would have actually a single-valued homogeneous chain with some kind of shorter distance, which is clearly not what is observed experimentally. And then sort of a derived challenge is that, yes? Hello?
No, it was just, I think,
a glitch.
Background noise.
Okay. So the other challenge is, of course, that you would have to come up with some kind of a mechanism of averaging out to the high temperature, high symmetry structure, which in case of spinels is relatively easy to sort of comprehend, because you have a pyrochlore sublattice that extends in 3 dimensions, and so these objects sort of randomize and end up into an average undistorted pyrochlore tetrahedral network. So to understand what is going on, particularly how to account for the long bond, because short bond we can understand as being sort of a weaker but still covalent bond between 2 titaniums, we refer to our theoretical theoretician colleagues, and so they have considered multiple configurations of this system as shown here. So you have ferroorbital ordered structure at which is the ground state, and it turns out that singlet triplet excitation corresponds to the energy scale of about 50 MeV. And then one can also consider anti-ferro orbitally ordered version, in which basically the magnetic excitation corresponds to energy of about 9 MeV. And so what basically they propose is that the transition can be understood as such that the orbital ordering changes character from ferro to antiferro, and that this is due to an abrupt jump in entropy. Sort of similar to, it's like an orbital analog of spin crossover system, in which magnetic ions basically have their spin state flipped from high spin to low spin. And then it turns out there is actually one other possibility, and that is that on each titanium, the orbital character is sort of mixed, both x, y, and zx, and that type of situation corresponds to magnetic excitations that are of the order of 5 MeV. In other words, you actually have possibly multiple states that are actually very close in energy and that are possibly competing. And as a result of competition between the states of antiferro orbitally ordered and this mixed orbital paramagnetic state, you might end up actually having, as a result, an appearance of defects, emergence of defects of XY ZX type, which in this particular case actually happen on an antiferro orbitally ordered background, and can be actually seen naturally as domain walls between two antiferro orbitally ordered domains. And then the other possibility, of course, is that you have this somehow you engage this third inert orbital through thermal fluctuations that could also serve as a defect. And so the significance of these defects is that they actually cause, in the case of this mixed orbital kind of variant, you end up with the longer bonds that correspond to, in this case, on average half an electron charge, or you end up with a long bond that corresponds to nominally 0 electron charge. So to summarize and rationalize, from the local structural perspective, we have a transition from long-range ordered spin singlet dimer state that looks like so, depicted on a chain, into a sort of short-range antiferro orbitally ordered state with defects of this type. And we coined the name dual or ODL state, which is presumably a prerequisite, or I'm sorry, precursor to the orbitally ordered dimerized regime at low temperature. And it exists, of course, in this multi-insulating regime. So that would pretty much be all that I have. I'm going to summarize and say that I hopefully showed you some convincing evidence that in this sodium titanium silicon to oxygen 6 pyroxene, there is an ODL-like precursor state, which is correlated over about 6 titanium sites. And that this implies that this precursor phenomenology extends to also to strongly correlated MOT insulators. This localized state is coming in as a response to electronic instabilities that are imposed by high symmetry crystal structure. As it turns out, the proximity of localized to itinerant crossover or metallic regime is not a prerequisite to have this state. They can actually form in the insulating systems as well, which might not be a surprise, but anyways. And as a kind of final statement, this type of precursor behavior might be actually ubiquitous in transition metal systems with partially filled D manifolds. And in considering the properties, one should also take into account this high temperature behavior. So with that, I will thank you for your attention. I would be happy to discuss it further.